The topic of the lecture is Structure of Metal and Alloys. The reference textbook is Richard Van Rood Introduction to Dental Material, 4th edition, from page 17 to page 22. There are two types of solidification, homogeneous nucleation and heterogeneous nucleation. Homogeneous nucleation when four atoms lose sufficient thermal energy and form nuclei and become able to form a unit cell. These unit cells will grow as more metal atoms reach a low enough energy to join on, and hence crystal formation occurs. This process is known as a homogeneous nucleation. It requires highly specialized equipment to grow a single crystal of metal from the entire melt. Heterogeneous nucleation, when solidification are initiated by impurities present in the metal and crystallization occurs. Boundaries between the crystals are called grain boundaries. Grain boundaries are essentially defects in the crystal structure of the metal. Heterogeneous nucleation, when solidifications are initiated by the process of solidification of a metal is shown in this figure. Fine-grained crystal size is desirable in a metal because it rises the yield stress. One way to promote a finer grain size is by rapid solidification, as used in casting of dental gold alloys into an investment mold that is held below the melting temperature. Alternatively, the process of many nucleating sites will give rise to the fine grain size. In dental gold alloys, the addition of iridium provides many sites of nucleation and act as a grain refining ingredient. Study the detailed structure of metals in terms of the sizes of the crystals, their shape, and their composition can be obtained by examining the metal surface under a light reflecting optical microscope. The action of chemicals on a polished surface, known as etching, can also reduce the amount of light reflected. A suitably chosen chemical will preferentially attack certain regions of the metal surface. These areas tend to be under high local stress, such as at the grain boundaries, where there is imperfect packing of the atoms. In effect, a groove is produced that will scatter the incident light and therefore show up as a dark line. Equiax is where all the grain are roughly the same size and shape. An example is hypoechoic stainless steel. Many other shapes and sizes of grains are possible, and these properties often depend on the method employed during solidification. For example, if molten metal is poured into a mold with a square or circle cross-section that is held at a temperature below the melting temperature of the metal, the grains could look something like that depicted in figure 1.4.4. Crystal growth will have the process from the walls of the mold toward the center. Deformation of metal is known as rot. It's when they are deformed by hammering, rolling, pressing, or drawing. Fusion of elements above their melting temperature producing a mixture of two or more elements is known as alloys. We have a binary alloy made of two elements and a ternary alloy made of three elements. Alloy consists of number of phases, where a phase is defined as a structurally homogeneous part of the system that is separated from other parts by defined physical boundaries. The common phases are gas, liquid, and solid. Examples are: water is a single phase, where water and oil is considered as two phases. A phase may have more than one component, as does saline, for instance, which is an aqueous solution of sodium chloride. Similarly, phases in metals can consist of a mixture of metals. Copper can contain up to 40% zinc without destroying its FCC structure. Such a solid solution, as it's called, will satisfy some special conditions. When two different metals are mixed together, the resultant material can be a single-phase alloy or a multi-phase alloy. This depends on the solubility of one element in another, and by the crystalline nature of the materials. The three solid phases are pure metal, solid solution, and intermetallic compound. Solid solution is a mixture of elements at the atomic level and is similar to a mixture of liquids which are soluble in one another. And there are two types: substitutional solid solution and interstitial solid solution. Substitutional solid solution: similar valency, similar crystal structure, atom size almost same. Example: gold in copper. The interstitial solid solution: atoms take spaces between solvent atoms. Solute atoms must be smaller than the solvent atoms. Example: iron and carbon. Intermetallic compounds: it occurs when two or more metals combine forming a specific composition. An example is dental amalgam alloy in some region of silver tin. A phase diagrams. Alloy can consist of a wide number of different phases depending on composition and temperature, and a means of representing it graphically has been developed. The vertical axis represents temperature, and the horizontal axis represents composition. Copper and nickel are close in the characteristics that they are readily substitutable for one another. This figure represents a single phase. The melting temperature falls between that of a pure copper and that of a pure nickel. The line which defines the transition from pure liquid to a mixture of liquid and solid is called liquidus, and the line which separates the mixture of solid and liquid from the solid is known as solidus. A pure metal solidifies. The transformation from a liquid to solid takes place at a well-defined district temperature. The plateau span's reason is the release of energy in the form of heat during the solidification process, which maintains the metal at a constant temperature. This energy is called the latent heat of fusion. When two metals are mixed to form an alloy, the alloy solidifies over a range of temperatures. The liquidus and solidus are now separate points on the cooling curve. Again, this is a comparison of a cooling curve between a pure metal and alloy, where pure metal shows pure metal characterized by latent heat of fusion, and alloy does not. By creating a series of the cooling curves of alloy for a range of compositions, it is possible to build up the phase diagram as shown schematically. Partial solid solubility: the components of materials are not sufficiently soluble to form a complete series of solid solution. The alpha phase consists of predominantly silver with a small amount of copper in it, and the beta phase consists of copper with a small amount of silver. The copper is able to dissolve in silver at a temperature of 780 degrees. Equilibrium phase diagram for silver-copper. The material will consist of two solid phases. Alpha phase consists of predominantly silver with a small amount of copper dissolved in it, whereas the beta phase consists of copper with a small amount of silver dissolved in it. An interesting and important feature is the depression of the temperature of the liquids at a composition of 72 silver to 28 copper at a temperature of 780 degree. This composition of the alloy can exist at three phases: alpha, beta, and liquid. This is called the eutectic point, and the temperature at the intersection of the three phases is the eutectic temperature. The composition is called eutectic composition of the alloy. The phase diagram of the iron-carbon system is called eutectoid reaction and differs only from the eutectic is that all three phases are solids. In non-equilibrium composition, phases with highest melting temperature will solidify first and form a lattice structure called dendrites. This formation of a solid with a non-uniform composition is known as segregation. Segregation can be eliminated by reheating to just below the melting, annealing. In systems with multiple phases, the phase with the highest melting temperature will always be the first to solidify, followed by the phases with lower melting temperature. As the first phase solidifies, it tends to form a lattice structure as a dendrite like in the figure. In summary, in order to obtain the best mechanical properties, alloy rather than pure metals are used in dentistry.